question number 1. It says, in general, the atomic mass of elements increase as the atomic number increases. Find the pairs of elements in the periodic table that are exceptions to this generalization. Now, I wasn't asking you to go through and find every exception, but there were a couple. Okay, that really, okay, well, that's wonderful. So, going from, let's see, potassium is 39.1, argon's 39.95. That's an example. When we look at cobalt going to nickel, the mass stays relatively the same. On some periodic tables, it's actually a little less. So in general, as the proton number increases, so does the mass. Looking at this, you'll see questions like this on the test Monday, whenever we meet again. And again, remember the periods are the rows. Okay, rows go this way. Groups and families are columns and go up and down. Also remember that you should know group 1A, 2A as alkali metals, alkali earth metals, and then 7A and 8A as halogens and noble gases. So those are the only 4 that actually have proper names associated with it. So if I were to ask you, if I were to ask you to identify something in a particular group or to name the group, make sure you know those 4. Everything else, whatever's on top of the column, like 3A, 4A, 5A, or even some B's. So A, did anybody have any issues with this? Okay, good. So easy points, right? Number 3, name the third period element that has a half-filled P. And had a few questions about this yesterday. And again, third period, so that represents the third row. And looking at the p orbitals, which are in this location, s over here, d down here, and f, of course, below, make sure that you know how many orbitals are actually in each of these. So s, there's 1, p, there's 3. So if it asks for a half-filled p, how many different electrons can go in the 3p orbitals total? 6. So half-filled is 3. So then you just count in 1, 2, 3, and hopefully phosphorus is your answer. Okay. And again, I often say this to a lot of students. Chemistry is not difficult. You guys just sometimes overthink it. Sometimes you're too smart for your own good at times. All right. Number 4 was an interesting question. It was just asking you to identify the group. And what it was wanting you to do was actually look at this, and this tells us how many valence electrons we have. So it's not coming out and asking for a particular energy level, but A is kind of shifty because it doesn't apply to row 1 or period 1. Because again, hydrogen and helium are on opposite sides. But everybody else, like 2A, 3A, 4A, and so on, okay, I'm sorry, 2s2, 3s2, 4s2, okay, that's what this is referring to, so those columns there. And again, there's 2 valence electrons, so that means that we're in group 2A, also known as the alkali earth metals. And then we have our S2P5, which tells us we have 7 valence electrons. So group 7A are also known as halogens. And then this one was interesting, electrons filling the d orbitals. It'll be a little better worded, but if you had as your answer 2B, you're on it. Okay. And again, most of the test will be multiple choice, so all the answers will be in front of you. There will be some math, of course, just like with the quiz. And then D, you have 2 electrons in the S and 6 in the P, so a total of 8. So that means that we're looking at group 8A, or the noble gases. 5 asks, how many valence electrons are in the following? So elements in the oxygen family, which is in column 6A, so 6. Sodium, group 1A, so there's 1. Elements in group 3A, period 5. I'm sorry, element in group 3A, period 5. So there's 3 valence electrons. That was the giveaway, the 3A. The element with the electron configuration, and again, looking at this one, how do we determine the number of valence electrons? It's the outermost s and p orbital electrons, so don't include the 1s2 or any others leading up to. So like if we went to the 3s, row 3, we would only focus on the outermost s and p orbitals, which again are valence only includes the row that the element's within. Okay. What are the electrons in the rows above called? Core electrons. Okay, so the valence electrons, core electrons. Which are easier to remove, valence or core? Valence. Okay. Core, is it impossible to remove?
No.
No, it just takes a lot of work and a lot of energy. Alright, so there'll be some editing there. Alright, looking at number 6, predict the number of protons and electrons in stable ions for iodine and radium. Now, I don't think radium's one of your 52, is it? Okay, sorry about that. That gives you a chance to go online and find out what these elements are. So iodine's right here. Let's start with the easy one. So we've got iodine right there. How many protons does iodine have? 53. Will that ever change? No, because the number of protons identifies what we're looking at. So iodine has 53 protons. That's a given. Now, stable ions, again, refers back to if it has 5 or more valence electrons, it'll gain to have 8 electrons, or if it's in 3 or less, it'll lose to have no electrons, no valence electrons. So iodine, which has how many valence electrons? 7 valence electrons. So if it needs how many more? Is it easier to gain 1 or lose 7? Gain 1. So what's its charge when it's a stable ion? -1. And again, ions are charges, so it's a charged particle. So in that case, if iodine has a -1 charge, how many electrons will it have? There you go. Okay. So coming over here to radium, what element number is it? 88. So how many protons? 88. What group is it in? Alkali earth, or 2A. So how many valence electrons does it have? 2. So is it easier to gain 6 or lose 2? So if it loses 2, how many electrons will it have? 86, and it'll be the same as radon. Okay. It'll have the same electron configuration as radon. Okay. Now, let me ask you this question, because sometimes a lot of people get this confused. If I lose 2 electrons on radium, is it going to behave the same way as radon? No, it will not. Okay, it just has the same number of electrons. That's it. Okay. It's what's the term when they have similar numbers of electrons or same configurations? Very good, isoelectronic. Make sure you know that term. You will hear me use that term a lot this year. All right. Number 7. What does the principal quantum number n designate? Energy levels, or the size of the orbital. There's also some more that we need to know. Actually, let's get some room here. So n represents the energy level or the size. Okay. So if you look at the periodic table, okay, so n equals 1, that's row 1. N equals 2, row 2. N equals 3, so on and so forth. So do the atoms get bigger as we go down a column or smaller? Bigger, okay? So the trend is they get larger because we're filling up electrons in those higher energy orbitals or more energy levels, let's just say that. And then if we look at the next letter, which is L, what does L represent? I know it wasn't in the homework, but you'll see it on the test, I promise. The shape, good. So shape, so you have your s orbitals, p orbitals, d orbitals, or your f orbitals. Okay. Now, that's all you need to know for that. And then m sub L, what's that represent? Orientation, very good. So whether it's along the x-axis, the y-axis, the z-axis, or a combination of those. Okay. So energy or size, shape, orientation, and then the last one, m sub s. What's that deal with? The spin, whether it's a positive spin or negative. Ooh, that's not how you're supposed to spin. Okay. So this is what we call the address for an electron. These are the quantum numbers. That's all you need to know. There are no numbers that we are associating with these values or these variables. In AP we will, but not in here. So just make sure you know those 4 quantum numbers, or actually letters to represent the quantum numbers. Okay. All right. Number 8, you'll be asked to do this all year long. Predict the common ions formed when atoms of the elements listed gain or lose electrons. So again, metals want to lose electrons and non-metals want to gain. So find it on the periodic table. So when we look at magnesium, magnesium's right here. So is it easier to gain 6 or lose 2? Lose 2, and it's isoelectronic with neon. Okay. So if it loses 2, it'll lose 1, 2. So it started with 12 electrons. If it loses 2 electrons, how many electrons will it then have? 10. And think that way, because there's 10. I think a lot of us are like, well, if I lose 2, that puts me at sodium. No, it's not the same configuration. Go through and do the quick mental math. If I gain 3 more electrons, okay, if I'm over here at phosphorus, if I gain 3 electrons, then I'm 1, 2, 3. Okay. All right. Chlorine is in group 7A, so it's easier to gain 1 than lose 7, so it'll have a -1 charge and be isoelectronic with argon. Aluminum in group 3A, it's easier to lose 3, so it's going to go in the opposite direction, even though you might say to yourself, man, that's a long way to travel. It's not about how far we go, it's how many do we have. So we have 3 valence electrons, so it's easier to lose those 3 than gain 5. Potassium is in group 1A, so it'll lose 1 electron, have a +1 charge. Sulfur, group 6A, will gain 2, have a -2 charge. Did you just break my chair?
Yeah.
So we can't lean back in these things. Barium with a +2, it's in group 2A, so it'll lose 2 electrons and have a +2 charge. And phosphorus, we already just mentioned that in the example there, is a -3 charge. All right, now the fun question. You guys, this probably was the class favorite of all of these. Okay? IE1, IE2, and IE3. IE is ionization energy. Now, we don't know what a mole is yet, so when you talk about ionization energy, it refers to the amount of energy needed to remove an electron. That's it. Don't worry about moles of electrons. That's a critter we'll talk about next semester. All right. So this one represents the first electron getting removed, that one represents the second, and then the third. What we're looking for is the big jump. Okay. And my rule of thumb is if it increases by over 4 times, okay, so 4 times the increase, that is considered the big jump. Okay. So when we look at ionization, the first one with 403, okay, so we have an ionization energy of 403, where the second one's 2632. Is that considered a big jump? Yeah. So what that means is the first electron is easy to remove from this atom. We don't know which of these 3 it is. However, the succeeding electrons are difficult. Translation. 1 is easy to remove. I can remove 1 from this group. Any additional electrons, I'm pulling from the core. Okay. So when you see a question like this, you don't want to sit here and go, well, how in the world are we going to know if that's gallium, rubidium, or barium? How are we going to know? Well, go to the column, because I'm not going to give you 2 options in the same column. And that's pretty typical when you get into AP. That's the type of question they're asking. So if we know the big jump occurs from the first to the second, that means that we're looking at a group 1A metal. Now, I did this to some students yesterday. Let's say that second ionization energy wasn't 2,632, but 632. Okay? Where does the big jump occur now? Between the second and third, which means, translation, 2 electrons are easy to remove. So if 2 electrons are easy to remove, you're going to group 2A. Okay, so look for the number of easy electrons to remove is how many, the group that it's in. Okay, so, and then so on and so forth. And I think I asked about 3 of these types of questions, just reworded it. So if we know that 1 electron is easy to remove, then we look for the element that's in group 1A. If it's in group 1A, then that means it's going to lose how many electrons? 1. Okay. And I don't think I asked for that, did I? No. Okay, just going over and above. All right, 10, use the position on the periodic table to determine the number of d orbital electrons for iron, zinc, and chromium. So iron, zinc, and chromium. So iron, the first one right here, how many electrons? 1, 2, 3, 4, 5, 6. Is it possible for us to take any s orbital electrons, place it in iron to get it to be half filled or full? No. Okay. So since if I add 1 or 2, then that means I've got 7 electrons or 8 electrons. I can't have 5 or 10. So iron is what it is. Okay. No special stabilities. And so iron looks it's argon 4s2, 3d6, so leave it. Zinc, well, zinc's nice. It's at the end. Okay, we don't even want to think about moving electrons. That doesn't make sense to move it from here to the P. We don't do that. We only move from S to the D. And since zinc's at the end of the row, we're not moving anything. It is happy, it's full. Whoop. Okay. However, chromium, that was the other one, right? So chromium's right here. How many d orbital electrons do we have initially? 1, 2, 3, 4. Ooh. Can we take one from the S and move it over? And you want to do that. If we were looking at, say, vanadium, would that work for vanadium? Yes. Okay, so again, while you're doing those electron configurations, for these two rows, okay, for these two rows in here, those are the only two rows that we care about for the special stabilities. Yeah?
So would vanadium be 4 instead of like 3?
Vanadium would actually be, let's do this. So argon, 4s0, 3d5, right? Because it starts with 1, 2, 3 d orbitals, and then we're going to take these two and move them over. Okay. So we can have a half filled by emptying out the S. Okay. And yeah, we're done with that one. And then find what is the electron or the element with the electron configurations. Now this one was kind of interesting. Okay. The 4s1, 3d5. Is it a good idea to go, oh, okay, 3d5, 1, 2, 3, 4, 5? Is that what we want to do? We want to say there's our 3d5? No, because we have one electron. So the best thing to do, especially on something like this, is count up how many electrons you have for that row. So you have 1 plus 5 is 6. So come over to the periodic table and go, okay, well, I'm starting here. 1, 2, 3, 4, 5, 6. There's my answer. Okay. Don't go, well, we're taking 1, so which one do we skip? Well, we don't skip anybody. We're counting in. We're moving it after the fact. Okay. All right. 12, it says, which transition metal, scandium with a +3 or zinc with a +2, is isoelectronic with argon? The way you answer this question is, make sure you know what isoelectronic means, that it has the same electron configuration. There's no way we're going to be able to get zinc with a +2 to have it with the same electron configuration as its nearest noble gas, because it has all of these d orbitals in play. The two electrons that are leaving are these guys here, okay? But it's not going to be isoelectronic with argon because it has all those d orbitals. Does that make sense? So scandium with a +3 charge, which is here, is scandium one of your 52? I think we answered that or asked that before. So this is going to be isoelectronic since we're going to lose 3 of those electrons, where zinc only loses 2, but still has all these d orbitals. 13, for which of the following elements do you expect there to be a very large increase going from the second to the third ionization energy? So again, going from the second to the third, we're predicting a very large jump in energy. So where is this element located? Which column? Second, yeah. So again, when it goes, the large jump is between the second and the third electron. That means that 2 are easy to remove. So whichever is in group 2, magnesium. Does that make sense? Okay. 14. What trend is observed for the atomic radius of atoms going down a group? So again, we talked about this earlier. As we go down a column or down a group, what's happening to the radius? It's getting bigger because we're putting more electrons in those higher energy orbitals. We're just filling up orbitals, so more electrons, bigger size. What happens as we go from left to right along a row? It decreases. Why does it decrease? Because it's becoming full with s and p orbital electrons. Now, here's what I don't want you to do. Use the same analogy or same reasoning that I used here. Well, we're getting more electrons. No. We're adding energy levels. We're adding more orbitals. Here, we're working with s and p orbitals. So as, it's kind of like, back when I had no money, I spend it like crazy. Now that I get more money, I'm like, I'm not spending it. I want more money. I don't want to spend it. And that's what these elements are doing. As they get more and more electrons, they're filling up their S&P orbitals. They're getting ready for retirement, so to speak. Okay? These are the young and free and could care less and like, I'll get more money sometime later. So as they start to fill up these orbitals, they become more and more possessive. They draw them closer and closer to the nucleus because they don't want to get rid of electrons. Non-metals want to get electrons. Metals, they're like making it easy, going, here's my electron. Come on. This is yours. Come and get it. Okay? So it gets smaller as we go from left to right. And we'll talk about a lot of fun things in AP Chem. The real reason with Coulombic attractions, the nuclear effective attraction. Oh my goodness, you're going to love it. Don't worry about question 15. That's more of a AP type thing. Okay. Don't worry about shielding. We're going to talk about that in AP. So I apologize for putting that on there. Did some of you Google that and find an answer? That's what my son does. He's in junior high. It's like, I don't know what to do. Like, nice. That's my boy there. All right. 16. What is the ionization energy and how is it determined? Now, this part was dirty. Not going to lie. But what is ionization energy? Okay, good. So it's the amount of energy needed to remove an electron. Okay. So it's the amount of energy needed to remove an electron. Don't worry about mole. I don't even know if I put the term mole in there. And how do you find it out? You go into the lab. You do experimentation. Wasn't that fun? All right, here's another IE question. Why does sodium have a why does sodium have a higher second ionization energy than first? Okay, so sodium has here's the amount of energy to remove the first electron. The second ionization energy is a lot higher. Why?
It's harder for it to gain one, it's easier for it to just lose one.
Okay, so anybody else want? Yes, Sage.
Because you're jumping all the way to a new energy level.
Okay. Where are we pulling the second electron from? The core. Very good. And keep that in mind, the core. It's kind of like I use it over and over again. That's what I do when I'm old. You can cut my hair. Those are valence electrons. No fight, no care. I really don't care. You can have the hair. But the heart is the core. It's going to take a lot of work and a lot of energy to remove that. So elements, once they give away their valence electron, or electrons, they're like, that's it. That's all you're going to get. Now we're going to fight to keep these guys. So in the rows above, those are going to stay with the atom. Once they fill up their S&P orbitals, elements don't want to get rid of those electrons. They may lose it in a battle, but they'll quickly get it back. Okay. All right. So they don't want to lose them. I won't ask a question like 18, but I just was trying to get the juices flowing in your mind there. Which is a larger radius, sodium with a +1 or neon? Okay, well, let me ask you this. Who has more electrons, sodium with a +1 charge or neon? Who has more electrons? Neither. They're the same, right? Okay, so they're isoelectronic with each other. However, sodium has something a little bit different. It has more protons. So it has more of a positive influence on those remaining electrons, on those 10 electrons. So if you think you have a more positive influence, what do you think you're going to do to that negative influence around it? Draw it in. Okay. So, and again, I won't ask you this type of question. I'll keep it, which is bigger, sodium or sodium with a +1 charge. That's what I'm going to ask you on the test. But this one's just to get you thinking. Okay, well, they have the same number of electrons, but sodium has more protons, so it's going to draw it in a little bit closer. This is what the test will be like. Which is bigger? Sodium, because it's more negative. Even though it's not negative, it's more negative than the +1 charge. Where are we at? 19? What trend in the ionic radius of an element would you predict as you move down? That's kind of a dumb question. So, yeah. Everything's going to get bigger as you go down the column. Let's just leave it at that. Which of the following would you predict to be larger? Whichever one's more negative, even though it's not negative. And then Fe plus 2 or Fe plus 3, the more negative. Okay. So that's how you answer those. Again, think about society. We're not a very nice society, but that's the way we think, and it's easy to remember that. The bigger you get, that's perceived as a negative connotation. The smaller you get, that's more of a positive. All right, and then configurations, you'll have to identify things. What if, let's do this. Let's say that you have this. I don't think I've ever talked about this. Good time to talk about it. Can that happen? I hear a sure. Let me ask you if it's ground state. What does ground state mean? Lowest energy level, where it's just relaxing, everything's okay. It is possible to remove one electron from a lower energy level to a higher energy level, but will it stay there? No, it'll return back. But this would be considered an excited atom. Okay, so this could happen for a brief moment of time as it's absorbing the energy. So if you see something that looks like that, don't freak out now. Again, don't confuse the s orbitals and d orbitals. But if you see something where you've got one strange electron in a higher energy level, or maybe even not 3s, but maybe even goes to 4s, okay, that ain't right. Okay, so that means that something has happened to that atom. It's been excited. It's absorbed energy. Okay, I don't know why I would mention that, but okay. All right, 23. Any questions or issues? If it's not one of your 52, just write the symbol. Again, it'll be multiple choice. Okay, but do know your 52 elements. Some of you are starting to slide on that, I've noticed. And then the math, which I think I've pretty much beat you guys down with on this. You'll see more of this on the test, I promise. So make sure you know what the values or the variables represent. Okay. Questions on any of that? Yeah, I'm sorry. Go ahead.
Are you going to be giving us like the formulas?
Oh yeah. You'll always get, I didn't put it on here, but I knew that you had access to it. I'll always give you the formulas, equations, and constants. You just have to know how to use them. I saw something, I'm not sure if it was somebody in this room. I have what's called a density triangle. I saw somebody use this on their test. I like it. I'm going to steal it and use it from now on. The E. Okay. Somebody used that, and then they also had, oh, not that one first. Okay. Everybody understand what that is? Okay. So speed of light, wavelength times frequency. Define frequency, it's speed of light divided by wavelength. Define wavelength, speed of light divided by frequency. Okay. Same thing over here. Even though we're not finding Planck's constant, E divided by V, you're not going to do it. But you will find energy, which is these two multiplied by each other, or frequency, that divided by that. I mean, I do it with a density triangle, but it really works with any three variable equation. So it's kind of nice. So for some of you who are challenged in rearranging variables, now later on we will be working with variables that have 5 in there, and you'll get to rearrange those. That's why I want you getting in the habit of rearranging variables. But not yet, not yet. Okay. And let's see. And then the last one. Or any questions about those? Go over the lecture notes. There's some things I know I didn't talk about in there. That wasn't on the review sheet. That was a pretty thick packet. So, and again, this test will have a staple, and you will need a calculator as well. Any last questions, concerns? Yeah. Couple, I think. I'm trying to remember. I haven't looked at it in a while. So maybe it's like discussing special stabilities, or maybe explaining a trend. So make sure you know your trends. And again, the trends are ionization energy, atomic radius. That's not a trend. Oh yeah, becoming more, well, that's not really a trend. There may only be two, really. Because talking about metallic properties, again, that becomes more important when we start writing chemical formulas. But you already know these are metals and these are non-metals, so that really isn't a trend. And I thought there was something else on there. It may have been electronegativities, but we haven't talked about that yet. So on the notes, I think we've only talked about two. So, but go back to the notes and check it out. I'm drawing a blank. Any other questions? Yes, Sage.
So did that review sheet basically cover everything, or?
I would say it got at least 80%. Yeah.
Okay.
Yeah. It's a good sampling. It's a good starting point. Definitely go back into the notes. And if you have any questions, email me. I've got a 7-hour drive one way to Missouri this weekend for a game, so I've got plenty of time. Yeah.
You know that core electrons that you're talking about?
Okay, hang on. Shh. Go ahead. Core electrons.
So are there only the noble gases?
Okay. When we talk about core electrons, the main reason why I say, okay, if you're writing the electron configuration and say we're looking at cobalt, we go up and over, because in that case we put the symbol argon, and that represents all of these orbitals over here considered core. So in the rows above, that's core electrons. Okay. So it's not just here, but this symbolizes, when I say bracket argon, then really what that means is it's 1s2, 2s2, 2p6, 3s2, 3p6. That's representing all of those orbitals with the electrons filled up. So when you hear me talk about core, it's different for each element, well, depending on what row they're in. So like for barium, all of these are considered core. These two are the valence. Does that make sense?
Yeah, I got it.
Yeah.
How would you determine the number of d orbital electrons in copper?
Copper? Okay. Well, copper is right here. Okay. So as it sits right now, before we do anything, how many d orbital electrons do you have? 9. Can we move 1 or 2 over to make it full and have S either half full or empty? How many will we move? 1. So in this case, copper would have 10 because of the special stabilities. Okay, so you always have to ask yourself, once you get to that spot, go, can I take 1 or 2 electrons from the S and move it over to make it either half filled, which is 5, or full, which is 10, in the d orbitals. Okay, and that only again applies to these 2 rows, which is nice.
So for zinc, it would just stay the same?
For who? Zinc, yeah. Zinc's all filled, so it has all of its S and D, so that's normal. Okay. Any others? Yeah, Brody.
So when writing those electron configurations,
Okay.
you always have to do that thing, go start with any of those 2 D rows,
Mhm.
3D, 4D.
Right. Yeah. So you always have to ask yourself, is it one of these 4 or one of these 4? Everybody else is normal. These are the ones that you have to go, it's got 8, I could bring 2 more over. It's got 9, I could bring 1 over. Okay. Yeah. Any others? Going once?